My name is Purushotham from EC department, working as assistant professor in MLRIT. So, previous class I explained about the what are the different types of AM modulators and AM demodulators. So today what I am going to cover in this lecture is first DSBSC modulation. What is the DSBSC modulation and what is the need of the DSBSC modulation? Why we are moving to the DSBSC modulation? Next, what is the mathematical expression for the generation of the DSBSC modulation? Next, what is the bandwidth? If you are using the DSBSC modulation, what is the bandwidth? So, what is the mathematical expression for the bandwidth? Next, what is the amount of the power required for the transmission of the DSBSC modulation system? So, I am starting now. So, the DSBSC modulation, in the process of amplitude modulation, we are transmitting carrier plus two sidebands. Carrier plus two sidebands. Those are upper sideband and lower sideband. So, the modulated wave has the information only in the sidebands. That is, the information is contained in the upper sideband and in the lower sideband. But the information does not contain in the carrier. So, the transmission of the signal which contains carrier along with two sidebands can be termed as a double sideband full carrier system. The transmission of the signal which contains carrier along with two sidebands can be treated as a double sideband full carrier system or simply DSBFC, double sideband full carrier system, which is similar to the amplitude modulation technique. So, here the problem is, if you are transmitting the carrier alone and transmitting the carrier with the sidebands, the amount of the power what is required for the transmission of the DSBSC, and if we are suppressing the carrier, and after suppressing the carrier, if you are transmitting, how much amount of the efficiency we are going to improve. So, here according to this block diagram what we have drawn here, it is containing the lower sideband, upper sideband and carrier, which is nothing but AM. That we are calling other name is nothing but DSBFC, double sideband full carrier system. So, today lecture what we are going to discuss is DSBSC, double sideband subtracted carrier system. So, we are suppressing the carrier. If we are suppressing the carrier, what are the advantages we are facing? So, the power required for the transmission of the carrier is very high. So, we are eliminating and we are suppressing the carrier. The power whatever we are using for the transmission of the carrier, if we are suppressing that carrier, that power we are saving, that saved power we are utilizing for the transmission of the upper sideband and lower sideband. In DSBSC, this carrier part we are eliminating or this part we are suppressing. Carrier alone we are suppressing. Carrier alone we are suppressing. And we are transmitting only the upper sideband and lower sideband. So, how much amount of the power we are saving? So, if we are taking the AM power expression, that is PT is equal to PC plus PT is equal to PC 1 plus mu square by 2. This is the expression for AM and DSBFC full carrier system. Here the terms what we are using is PC plus PC mu square by 2. So, this is the carrier. This one is the sidebands. Sidebands, both upper USB plus LSB. So, in DSBSC, only sidebands we are transmitting. So, in DSBSC, only side bands we are transmitting. Side bands only we are transmitting. So the power containing in DSBSC is PC mu square by 2. As per the efficiency of the AM, if you are calculating sideband powers by total power. So what is the sideband power? Sideband power is PC mu square by 2. What is the total power? PC 1 plus mu square by 2. So if we are substituting this one, PC mu square by 2 divided by PC will cancel 1 plus mu square by 2. So here this expression I am writing as mu square by 2 plus mu square. The power efficiency of the DSBSC or AM can be represented as a mu square by 2 plus mu square. So if mu is equal to 1, so what is the efficiency we are getting? 1 by 3, that is 33.3% efficiency. So what is the efficiency? 33.3% efficiency. What is the meaning of that? Among the total transmitted power, only 33.3% of the total transmitted power is containing the useful information that is related to the side bands. So this is the sideband power and useful power. So what is the remaining? Remaining is 66.6%. 66.6% of the power is concentrated in carrier. 66.6% of the power is concentrated in the carrier. So if we are removing or suppressing the carrier, how much amount of the power we are saving? 66.6% of the power we are saving by removing the carrier. Why? The carrier does not contain any information. So carrier alone we are not at all transmitting in DSBSC modulation system. Carrier we are suppressing. So we are saving the 66.6% of the power. The saved power can be effectively utilized for the upper sideband and lower sideband transmission. Okay, this is the main advantage of the DSBSC modulation system. So then what is the mathematical expression for the generation of the DSBSC system? So here DSBSC system, there are two signals are there. Okay, first M of t is the modulating signal. We are applying to the product to modulator. This is the product to modulator. Another input we are applying is a AC cos 25 FCT. M of t, how we are representing? M of t is nothing but AM cos 25 FMT. M of t is nothing but AM cos 25 FMT. C of t is nothing but AC cos 25 FCT. So carrier which is containing the high frequency, carrier frequency is high frequency. So this high frequency carrier characteristics we are changing according to the modulating signal. Okay, amplitude of the carrier we are changing. High frequency amplitude of the carrier we are changing according to the modulating signal, and output is DSBSC wave that we are representing as a S of t. S of t is nothing but C of t into M of t. C of t into M of t. So see here, modulating signal AM cos 25 FMT, carrier signal AC cos 25 FCT. Those two signals we are applying to the product modulator. Output of the product modulator is S of t. S of t can be represented as M of t into C of t. So what is the expression? M of t is nothing but Am cos 2 pi fmt. S of t is Ac cos 2 pi fct. If you are multiplying both signals, Am Ac cos 2 phi fmt cos 2 phi fct. Okay, this is the mathematical expression for the DSBSC modulated signal. DSBSC modulated signal. So now let us calculate the bandwidth. Already we have calculated the bandwidth for the AM. What is the formula we have used there? Bandwidth is equal to F max minus F min. Bandwidth is nothing but F max minus F min formula we are using. So in the DSBSC, what is the F max and what is the F min? Okay, to know the expression or the formula for the F max and F min, what are the component it is containing? So first modulated signal S of t expression we are taking, that is Am Ac cos 2 pi fmt cos 2 pi fct. So this expression is in the form of cos A cos B. This expression is in the form of cos A cos B. Cos A cos B, that is nothing but is equal to cos A plus B plus cos A minus B. Cos A plus B plus cos A minus B. A plus B plus cos A minus B over 2. Okay. Actually, the formula is 2 cos A cos B is equal to cos A plus B plus cos A minus B by 2. So now this expression I am representing in the expanded form. So now Am Ac by 2 cos 2 pi Fc plus Fm. A is nothing but A is equal to Fc. B is nothing but Fm. Okay, A plus B, Fc plus Fm, A minus B, Fc minus Fm. So Am Ac by 2 cos 2 pi Fc plus Fm into plus Am Ac by 2 cos 2 pi Fc minus Fm into T. This expression we are getting. Okay, so in this expression Fc plus Fm, this we are calling it as a F max, which is nothing but USB, upper side band, and this term we are calling it as a F minimum. F minimum, this is nothing but LSB, lower side band. Okay, so according to the formula bandwidth calculation, we are using bandwidth is equal to F maximum minus F minimum. So this is the F maximum, Fc plus Fm, F maximum, and Fc minus Fm, F minimum. So you are substituting F maximum Fc plus Fm minus of Fc minus Fm. So what is the value we are getting here? Fc plus Fm minus Fc plus Fm. Minus Fc will cancel. So finally, what is the expression we are getting? 2Fm is the bandwidth for the transmission of the DSBSC. So the bandwidth for the AM and bandwidth for the DSBSC both are same. So this is the expression for the bandwidth. So next, what is the power required for the transmission of the DSBSC and what is the mathematical expression for the power calculation? So here consider the following equation. The S of t DSBSC modulated signal expression we have taken, that is AC AM by 2 cos 2 pi Fc plus Fm into T plus AM AC by 2 cos 2 pi Fc minus Fm into T. Okay, this is the DSBSC modulated signal. So now after implementing the cos formula and finalized expression, you have taken this one. So now here it is containing the USB, that is nothing but total power S of t, which is containing the total power PT, which is nothing but P USB power required for the transmission of the USB, power required for the transmission of the LSB. Power required for the transmission of the LSB. So here this is the amplitude of the signal. This signal what we are calling Vmax, Vm. This is also what we are calling Vm, maximum signal. Okay. So we know the formula P is equal to power expression V square by R. So the RMS power we are taking Vrms square by R. So what is the formula for Vrms? Vrms is equal to Vm by root 2. Vrms is equal to Vm by root 2. So what is the Vm? Vm is nothing but here Vm can be represented as Am AC by 2. So here Vm is nothing but Am AC by 2 root 2. Okay. So the power expression is Vrms square by R. Vrms square by R. So here P USB. This is the USB. This is nothing but USB. Upper side band FC plus FM. So this is nothing but lower side band LSB. So P USB is nothing but AM AC by 2 root 2 old square. This old square by R. So here R is equal to, let us assume 1 ohm. R is equal to 1 ohm. So what is the final expression we are getting? AM square AC square by 8R. AM square AC square by 8R. This is the PUSB power. Similar to the lower side band P LSB power is equal to AM square AC square by 8R. AM square AC square by 8R. Okay. So if R is equal to 1, automatically what is the value we are getting? So PUSB plus P LSB, that is AM square AC square by 8R plus AM square AC square by 8R. So final expression what is getting? AM square AC square by 4R. So let us take AM square AC square by 4. So R is equal to 1 means the power for the transmission of the DSBSC is AM square AC square by 4. So this is nothing but PC AM square by 2. What is the PC? PC is the carrier power, which is nothing but AC square by 2. PC is the carrier power, which is nothing but AC square by 2. So PC AM square by 2 or AM square AC square by 4 is the power required for the transmission of the DSBSC signal. Okay. So this is the about the power required expression. So today lecture what I have covered. So first, what is the DSBSC modulation and what is the need of the DSBSC modulation and what is the mathematical expression for the bandwidth calculation. We have calculated bandwidth, that is F max minus F min, which is nothing but 2 FM. The bandwidth what we are calculated for the DSBSC and bandwidth whatever we are calculated for the AM or DSBFC. DSBFC means double sideband full carrier system, which is same as the AM. Other name for DSBFC is nothing but AM. So bandwidth for that is 2 FM. And DSBSC double sideband suppressed carrier system is equal to 2 FM. Same bandwidth is required for the transmission of the AM, transmission of the DSBSC. And other thing is nothing but power. So what is the expression for the power? AM square AC square by 4 is the power. So by using the DSBSC, main advantage is the carrier what we are suppressing. By suppressing the carrier, we are saving the 66.6% of the power. So that power we are utilizing for the effective transmission of the two side bands, that is lower side band and upper side band. Okay, so we will meet you in the next class. Thank you.